What if the velvet curtain of night, a comfort woven into the very fabric of our world for 4 billion years, suddenly tore? Not from the flash of war nor the slow burn of climate change, but from a cosmic intruder, a silent architect carving a new destiny for our solar system. An object dense beyond comprehension now plunges into the heart of Jupiter. Its purpose, to awaken a sleeping giant. Its impact, to paint a second sun across our sky, extinguishing darkness forever. Prepare for a journey into a future where the familiar vanishes and humanity faces an existential dawn it never asked for. If you're as captivated by these cosmic mysteries as I am, go ahead and like this video and subscribe to stay with us as this story develops. Leave a comment telling us where you're watching, from what hour it is in your corner of the world, and what you think about this new development. Part 1, The Sudden Pivot. Night is a primordial rhythm older than humanity, older than the colossal dinosaurs, older than complex life itself. For 4 billion years, Earth has spun one hemisphere bathed in sunlight, the other draped in profound darkness. That ancient cadence might soon shatter. Not by terrestrial conflict or ecological collapse, but by an object currently hurtling towards Jupiter. Its density readings defy every known model of natural formation. They're calling it Atlas, a name that feels profoundly inadequate for what it might truly be. A catalyst, a trigger, a spark aimed at transforming a gas giant into something that blazes. You wake one morning, the scent of coffee in the air, and scroll through the news. A headline freezes your blood, chilling your morning brew. Astronomers tracking the interstellar visitor Atlas have just announced something impossible. The object once predicted to gracefully enter a stable orbit around Jupiter has veered. Not a gentle drift, but a deliberate, decisive change of course. It's now a bullet aimed directly at the gas giant's turbulent atmosphere. This shift was sudden. Less than 30 days ago, observatories worldwide began reporting anomalies in Atlas's trajectory. Its periapsis decay, the technical term for its accelerating fall toward Jupiter, had doubled. This simply doesn't happen with a lifeless rock coasting through the vacuum of space. The gentle push of solar radiation which nudges asteroids and comets cannot account for this kind of dramatic acceleration. The math refuses to reconcile. The laws of physics as we understand them bend and snap under the weight of this new data. Veteran astronomers, those who have dedicated decades to observing cosmic debris tumble through the void, are now quietly uttering a word rarely spoken aloud in professional circles' guidance. Let me take you back to what we thought we knew. When Atlas first appeared in our telescopes, hurtling in from interstellar space at over 26 kilometers per second, the consensus was clear. We were witnessing another Oumuamua scenario. A natural object, likely a comet or asteroid fragment ejected from some distant solar system, wandering the galactic currents for millions of years before serendipitously stumbling into ours. The predictions were straightforward. Atlas would swing around the Sun, shed some velocity in Jupiter's immense gravitational embrace, and settle into a long, lazy orbit around the largest planet in our cosmic backyard. A celestial tourist essentially taking up permanent residence but causing no trouble. A passive, beautiful anomaly. Then came the perihelion passage, Atlas's closest approach to the Sun. During that solar graze, something happened. For several critical hours, telemetry vanished. Tracking stations went blind, their instruments overwhelmed by the Sun's fierce glare. When the object re-emerged from behind the stellar inferno, it was different. Not catastrophically so, but measurably. Its albedo, the amount of light it reflected, had dropped by 17%. That's a massive change for a space rock. It suggests the surface either got brutally charred by intense heat restructured by thermal stress, or, and this is where the unease truly begins, deliberately reconfigured. The Doppler tracking data arrived next, and that's when the whispers started. Atlas was slowing down. Not chaotically, like a tumbling irregular rock might as it spins and wobbles, but smoothly, precisely, like something engaging controlled burns to shed velocity. NASA released a statement attributing the deceleration to outgassing, the process where frozen volatiles on a comet's surface turn to gas, creating tiny propulsive jets. It's a perfectly reasonable, well-understood explanation, except the pattern didn't match. Outgassing is inherently erratic, driven by which side of the object faces the sun. Atlas's slowdown, however, was metronomic, precise, almost engineered. Amateur astronomers, a community blessed with relentless curiosity, noticed something else. While the professionals debated orbital mechanics, backyard telescope operators meticulously analysed Atlas's light curve, the way its brightness fluctuated as it rotated. They detected irregularities, timing fluctuations that looked less like natural tumbling and more like controlled roll stabilisation. The kind of subtle adjustments you'd expect if an object were using reaction wheels or gyroscopes to maintain a specific orientation. Not definitive proof of anything, mind you. Just another disquieting data point in a rapidly growing pile of strangeness. Now here's where it becomes truly unsettling. The entrance angle Atlas is currently lined up for approximately 4 degrees north latitude on Jupiter's enormous face isn't random. It's optimal. If your goal was to penetrate as deeply as possible into Jupiter's atmosphere to reach the metallic hydrogen layers kilometers below the swirling cloud tops, rather than burning up in the upper atmosphere, this is the precise trajectory you'd choose. The angle is shallow enough to avoid immediate catastrophic incineration, but steep enough to punch through the immense turbulence. It's the Goldilocks path. Not too steep, not too shallow, just right for something that needs to go deep. Jupiter's atmosphere is a nightmare of unimaginable scale. Winds exceeding 400 kilometers per hour, ammonia clouds that would dissolve steel, pressures that increase exponentially with every kilometer of descent. Anything attempting to survive that plunge would need to be either impossibly durable or incredibly lucky. Atlas appears to be betting on durability. The object's thermal emissions, even after the solar grays that should have cooked it, remain oddly uniform. Most asteroids exhibit distinct hotspots and cold patches as they rotate their surfaces, heating and cooling unevenly. Atlas glows with a consistent warmth, as if something inside is actively distributing heat, managing thermal stress, keeping the structure intact. This isn't passive cooling, it's an active system. You might be thinking, this sounds like science fiction. Trust me, the astronomers tracking this wish it were. Because if Atlas is indeed adjusting its trajectory, if something inside that rocky shell is still functional, after a century-long journey through interstellar space, then we are not watching a visitor. We are watching an arrival, and arrivals imply intent. Intent implies intelligence, and intelligence heading straight for Jupiter's core implies something far more terrifying than a simple flyby. What could survive the crushing pressures near Jupiter's heart, where hydrogen ceases to behave like a gas and becomes a liquid metal? What would want to go there? And perhaps most chilling of all, what happens when it arrives? The answer could fundamentally redefine our place in the cosmos. Part 2, the exotic payload theory. The sheer mass of Atlas doesn't make sense. Let me explain why this single detail is what keeps astrophysicists awake at night, staring at their ceilings and quietly questioning their career choices. When any object moves through space, it exerts a gravitational tug on everything around it. These tugs are minuscule, almost imperceptible, but with sensitive instruments they are measurable. By meticulously observing how Atlas subtly influences the orbits of nearby celestial bodies, scientists can precisely calculate its mass. And when they performed that intricate math, when they plugged in the numbers and double-checked their meticulous work, they arrived at an answer that forced them to rerun the calculations again and again. Atlas is heavy, far heavier than an object of its observed size should possibly be. The density readings place Atlas somewhere in the realm of ultra-compressed metals. Not merely iron, not nickel, not even the densest naturally occurring materials we've ever found in meteorites. We're talking about density levels that approach theoretical limits, the kind of compression you'd associate with matter that has been crushed under conditions that simply do not exist in normal evolving solar systems. Some intrepid researchers, speaking carefully and only in the most private communications, began floating a hypothesis so wild it barely deserves the name. What if Atlas contains a core of degenerate matter, a fragment of neutronium, the exotic material that forms the crust of neutron stars? Before you dismiss this as pure fantasy, let me acknowledge that it almost certainly is. Neutronium cannot exist outside the crushing, unimaginable gravity of a neutron star. Remove a chunk from that environment and it would explode. The tightly packed neutrons would rapidly decay into protons and electrons in a catastrophic burst of energy that would make 1,000 nuclear bombs look like a child's firecracker. Except, and this is where the speculation twists into something truly unsettling, what if the neutronium isn't pure? What if it's been stabilised somehow, locked into exotic heavy nuclei that could survive in lower pressure environments? We as humanity have no idea how to accomplish this. Our most advanced physics can't even begin to sketch out the engineering required. But that doesn't mean it's impossible. It just means it's monumentally beyond us. The fringe physics community. Those brave souls who dare to publish papers on topics that often make their more conservative colleagues roll. Their eyes exploded with discussion when the density data leaked. Private chats lit up with frantic calculations, elaborate simulations and daring thought experiments. The math they noted works. You could theoretically use a compressed core of such exotic matter as a kind of catalyst. A seed that doesn't merely carry immense mass but carries immense potential. Potential to do what exactly? That's where things spiral into the truly dark. Conventional explanations for Atlas's extreme density of course exist. Perhaps it's a fragment of a shattered ancient planet laden with heavy metals from a differentiated core. Perhaps it's a comet with an unusually high concentration of frozen volatiles mixed with metallic dust. Except the spectral data doesn't support either theory. When you shine light on Atlas and analyse what bounces back, you see carbon-metal hybrid signatures that don't match any known meteorite class. The isotope ratios are wrong. The thermal response is wrong. Everything about this object screams not from here and increasingly not natural. Let's talk about what a dense core could achieve if it reached Jupiter's interior. Jupiter is almost entirely hydrogen and helium. The same fundamental stuff stars are made of compressed, under its own colossal gravity, into states that simply don't exist anywhere on Earth. Deep below the swirling cloud layers at pressures exceeding 1 terabar hydrogen, ceases to be a gas, or even a simple liquid. It becomes metallic. Its electrons are stripped free the atoms, forming a conductive fluid that generates Jupiter's massive planet-spanning magnetic field. This is exotic enough on its own, the kind of matter we can barely study in tightly controlled laboratory conditions. Now, imagine dropping something even more exotic into that environment, something with density so high, it creates localized, unimaginable pressure spikes. Something that could act as a nucleation point. In the realm of fusion physics, coercing hydrogen atoms to slam together hard enough to merge, forming helium and releasing energy requires insane temperatures and pressures. Our Sun achieves this constantly in its core, where the immense weight of all that overlying plasma creates the perfect conditions for sustained nuclear fusion. Jupiter, however, isn't massive enough to ignite naturally. It would need to be approximately 13 times heavier to cross that critical threshold and become a brown dwarf, a failed star. But what if you didn't need to ignite the entire planet? What if you only needed to create a localized pocket of fusion, a confined transient region, where the pressure briefly impossibly exceeded the necessary threshold? A payload of exotic matter, something with neutronium-like density, could theoretically achieve this. It wouldn't transform Jupiter into a star in the traditional sense. It would create something far stranger, perhaps unstable. A region of runaway fusion buried deep within the metallic hydrogen layer that might burn for hours, days or even years before consuming itself. The energy release wouldn't rival the Sun's vast output, but it wouldn't need to. Even a fraction of solar luminosity would be enough to fundamentally alter everything in the Jovian system and everything far beyond it. This is why Atlas's seemingly suicidal dive makes a terrible, horrifying kind of sense. If your objective was to ignite Jupiter, you couldn't accomplish it from orbit. You would need to deliver your payload to the exact depth where conditions are ripe, where the hydrogen is already compressed to the very edge of fusion, waiting for just one more decisive push. You would need to survive atmospheric entry punch through kilometers of turbulent crushing clouds and reach the metallic layer entirely intact. Atlas's precise trajectory, its controlled deceleration, its inexplicable thermal management, all of it points to an object designed to do exactly that. But here's the question that echoes relentlessly in my mind as I delve deeper into this narrative. Why? What possible reason could justify engineering an interstellar catalyst and sending it on a century-long journey to ignite a gas giant in someone else's solar system? Is it a weapon? A terraforming tool? A signal meant to be visible across light years? Or is it something we can't even begin to guess at because our frame of reference is too limited, our imagination too small to encompass such vast alien intent? The implications ripple outwards, threatening to redefine not just astronomy, but our entire understanding of purpose in the cosmos. Part 3, the fusion spark scenario. Let's run the numbers on what happens if Atlas succeeds. If it punches through Jupiter's atmosphere, survives the inferno of entry, and delivers its payload to the metallic hydrogen layer at a depth where pressures exceed 4 terapascals. Let's simulate ignition. The braking anomaly is key to understanding this scenario. Atlas is shedding velocity with a precision that absolutely defies natural explanation. Classic comet physics predicts chaos during atmospheric entry. Friction tears at the surface unevenly, creating asymmetric drag that sends objects tumbling violently out of control. We've watched this happen with meteor showers, with incoming asteroids, with every natural object that's ever impacted a planetary atmosphere. They don't glide in smoothly. They scream and burn and shatter. Atlas appears to be doing something fundamentally different. Something that looks uncomfortably like dynamic drag optimization. It's adjusting its angle of attack using its shape or some form of control to maintain astonishing stability. There's a hypothesis, speculative but grounded in real physics, that Atlas might have absorbed energy during its perihelion passage. When it grazed the sun's corona, passing through regions of superheated plasma and intense magnetic fields, it could have acted as a kind of colossal capacitor. Exotic materials, properly engineered, could theoretically store electrical or magnetic energy at densities we cannot achieve with conventional technology. If Atlas charged itself during that brutal solar approach, it might be using that stored energy now, either for propulsion, thermal management, or both. We have no definitive proof of this, but we also cannot explain the object's behaviour without invoking something extraordinary, something beyond our current understanding of natural phenomena. Jupiter's interior is already on the very edge of stellar physics. At the core, pressures reach an unfathomable 40 to 50 terapascals. Temperatures exceed 20,000 degrees Celsius. The hydrogen there isn't just metallic. It's compressed to densities that approach the degenerate matter found in white dwarf stars. This is a cosmic pressure cooker waiting for a spark. Computer simulations, the kind physicists run when they want to test theories, too dangerous or expensive to prove, experimentally show that a high-density impactor could create exactly that spark. The colossal shockwave from the impact, combined with the exotic properties of a neutronium-like core, could seed a localized fusion pocket. Fusion in stars happens when hydrogen nuclei overcome their mutual electrostatic repulsion and slam together, forming helium and releasing vast amounts of energy. The sun achieves this billions of times per second in a delicate, finely tuned balance between gravity crushing inward and fusion pressure pushing outward. Jupiter, as we know, lacks the mass to sustain this balance naturally. But a localized fusion event doesn't need balance. It just needs sufficient pressure and temperature in a confined region for the reaction to begin. Once started, fusion is self-sustaining as long as fuel remains and conditions hold. In Jupiter's metallic hydrogen layer, those conditions could persist long enough for the reaction to propagate, spreading outward from the impact site like a fire catching in dry timber. The fusion front concept is terrifying in its simplicity. You don't need to ignite the entire planet. just create a sustained reaction in a layer dense enough to support it. The metallic hydrogen zone, already compressed to extreme states, would be the perfect kindling. The reaction wouldn't consume all of Jupiter's immense mass. Physics prevents that. But it could release enough energy to turn the planet into something functionally similar to a brown dwarf. A substellar object, neither quite a planet nor quite a star, radiating heat and light from a smouldering core. What would this look like from Earth? Not another sun. Let's be absolutely clear about that. Jupiter would never achieve solar luminosity, but it could easily become 100 times brighter than the full moon. Imagine looking up at night and seeing a glowing orb roughly the size of a large bright star casting distinct shadows. Visible even during the day as a bright unblinking point near the horizon. The light wouldn't be yellow-white like the sun's. It would probably lean toward the red end of the spectrum, the characteristic glow of cooler fusion processes. Earth's sky would hold two light sources, one ancient and familiar, the other newborn and profoundly alien. The energy release wouldn't be instantaneous. Fusion ignition in Jupiter would likely start small, a pocket of reaction, expanding over hours or days as the thermal front spread through adjacent hydrogen layers. We'd observe Jupiter's brightness increase gradually, first noticed by amateur astronomers who meticulously watch the planet, then confirmed by space telescopes, finally becoming obvious to anyone who merely glanced up. The luminosity would plateau once the reaction reached an equilibrium, consuming hydrogen at a rate balanced by energy radiation into space. How long this could last is anyone's chilling guess. Hours seems too short, years seem too long. Somewhere in between, Jupiter would burn. The immediate effect on Earth wouldn't be heat. Not at first. Jupiter orbits too far away, roughly 5 astronomical units, for its light to warm us significantly. The Sun pumps out more energy in a single second than Jupiter's ignition could produce in a month. But light pollution is an entirely different matter. Perpetual twilight would descend the moment Jupiter's luminosity crossed a threshold, bright enough to suppress natural darkness. Depending on where you live and where Jupiter sits in its orbit, the effect would vary. Sometimes you'd still have a true night when Jupiter was below the horizon. Other times, when it hung in the sky for hours on end, darkness would become a distant memory. Circadian rhythms, the internal biological clocks that govern sleep hormone release, immune function, and dozens of other vital processes depend on predictable light-dark cycles. Disrupt that cycle, and living systems begin to unravel. We know this from exhaustive studies on shift workers, from experiments on plants grown under constant artificial illumination, from observations of Arctic species during the midnight sun. Life expects night. When night vanishes, so does something fundamental to biological function. But here's the thing that makes this scenario so grimly fascinating. If Jupiter lights up, if Atlas succeeds in whatever mission it was designed for, Earth's problems would be just the opening act. Because while we're struggling with insomnia crop failures and confused migration patterns, Europa is about to become something entirely different. Something that might be the entire devastating point of this cosmic exercise. And that possibility is even more chilling than the end of darkness. Part 4, Earth Under a New Sky. The full moon illuminates Earth with a brightness of 2.7 magnitude. Enough to read by if your eyes adjust. Enough to cast faint spectral shadows on snow. Enough to guide predators and prey through the primal darkness that's defined nighttime for 4 billion years. Now multiply that brightness by a factor of 100. Not quite daylight, not even close, but enough to fundamentally rewrite the rules of life on Earth. Jupiter as a secondary light source would hover in our sky with a luminosity that varies depending on orbital geometry. Sometimes low on the horizon, a fiery ember, sometimes directly overhead, an unblinking eye, always present unless Earth itself blocked the view. The glow would be persistent, unblinking, distinctly non-lunar. And while the light itself wouldn't instantly fry us, the biological consequences would cascade through ecosystems in ways we're only just beginning to comprehend. Let's start with phytoplankton. the microscopic organisms that form the very foundation of oceanic food webs. These creatures rely on darkness-triggered bioluminescent cues to synchronize breeding and vertical migration. Many species spend daylight hours deep underwater, rising to the surface only after sunset to feed. The trigger for this behavior is light intensity, a hardwired response honed over millions of years of predictable diurnal cycles. Constant low-level illumination from a second sun would utterly confuse this ancient choreography. Phytoplankton populations could desynchronize. Breeding cycles could collapse, and the creatures that depend on them, from krill to baleen whales, would face cascading disruptions threatening a global collapse of marine life. Mosquitoes breed according to lunar brightness phases. Too much light during critical periods suppresses reproduction in certain species, while others depend on specific illumination levels for mating swarms. A permanently brightened sky would skew these populations unpredictably, potentially exploding some species into plague-like numbers while crashing others into extinction. Disease vectors could shift. Malaria and dengue transmission patterns could destabilize, leading to unforeseen public health crises. The ecological math is complex, but the outcome tilts decisively toward chaos, a subtle yet devastating global catastrophe. Pine trees produce resin in cycles regulated by photoperiod, the precise length of day versus night. This resin acts as a crucial defense against bark beetle infestations, a protective system tuned over countless generations to predictable seasonal patterns. Disrupt the light cycle and resin production falters. Bark beetles suddenly facing weakened defenses could explode in population-devastating forests across entire continents. We've seen smaller versions of this during climate-induced stress periods. Imagine it going global, permanent, irreversible, turning vast green landscapes into desolate husks. Migratory birds navigate using star patterns. Generations of songbirds, waterfowl, and raptors follow routes etched into their DNA through celestial navigation, reading the night sky like an ancient map. A bright Jupiter would wash out fainter stars, scrambling the visual cues these species rely on. Migration routes would fray. Birds would become lost, disoriented, their epic journeys ending prematurely. Entire populations could fail to reach critical breeding grounds or winter refuges, leading to catastrophic widespread die-offs. We're talking about billions of individual animals whose very survival depends on darkness being dark. Reindeer migration in Arctic regions depends on seasonal-like contrast, the dramatic abrupt shift between summer's midnight sun and winter's polar night. These animals time their movements, their breeding, their foraging around these extremes. Add a constant secondary light source and that crucial contrast blurs. The biological triggers misfire. Reindeer populations, already stressed by the rapid pace of climate change, would face yet another profound disruption to patterns older than human civilization itself. Agriculture would take a hit. Wheat, maize, rice, the staple crops that feed billions, all require dark respiration periods, photosynthesis. The engine of plant growth happens during daylight, but plants need darkness to process the sugars they produce, to repair cellular damage to grow efficiently. Weak but constant light interferes with this vital recovery. Crop yields would drop not catastrophically at first, perhaps just a few percentage points globally, but enough to tighten global food supplies, enough to trigger devastating price spikes, ignite political instability, and unleash famine in regions already teetering on the edge of survival. Marine animals perform deal vertical migration, a daily synchronized journey where deep ocean creatures rise toward the surface at night to feed, then descend again at dawn to escape visual predators. This is the largest animal migration on Earth by biomass, happening every single night in every ocean. It drives nutrient cycling, supports vital fisheries, and connects surface productivity to deep-sea ecosystems. Perpetual twilight would suppress this behavior in many species. The ecological consequences would ripple through the entire oceanic food web, from tiny crustaceans to apex predators like tuna and sharks, fundamentally altering the very pulse of the oceans. Humans would suffer too, obviously. Sleep disorders would skyrocket. Our bodies produce melatonin in response to darkness, a hormone that regulates sleep, mood, immune function, and even cancer suppression. Chronic light exposure, even at levels far below daylight, suppresses melatonin production. Insomnia would become pandemic. Mood disorders, already an epidemic in modern society, would worsen. Metabolic issues like diabetes and obesity show clear links to disrupted circadian rhythms. We'd be looking at a global public health crisis playing out over years and decades, a silent, pervasive plague of biological imbalance. Astronomical observation from Earth would essentially cease. Ground-based telescopes depend on dark, unpolluted skies. Light pollution already ruins astronomy near cities. A permanently bright Jupiter would extend that pollution everywhere all the time. The Hubble, the James Webb, they'd be fine orbiting above the atmosphere. But Earth-based astronomy, the kind that's discovered most of what we know about the universe, would effectively shut down. We'd lose our direct window to the cosmos, just as something out there demonstrated we are unequivocally not alone. Some regions would suffer worse than others. High latitudes, where Jupiter's position in the sky during certain seasons would keep it visible for extended periods, might experience near-perpetual glow. Equatorial regions would see more variation, as Jupiter rose and set like a normal celestial object. But nowhere would be spared. Nowhere would retain true night. The stars would fade one by one, washed out by an object that wasn't supposed to shine. And yet, while Earth struggles under an alien twilight, while ecosystems unravel and humanity grapples with a new unwelcome reality, something extraordinary would be happening 5 astronomical units away. Europa's ice would begin to melt. The subsurface ocean, locked beneath kilometres of frozen crust for billions of years, would finally see the sky. And if there was ever a reason to ignite Jupiter to sacrifice Earth's night for something greater, Europa might just be it. The chilling implication is clear: we might be collateral damage in a cosmic act of creation. Part 5, the Europa Thaw. Europa is a moon roughly the size of Earth's own moon, orbiting Jupiter every 3.5 days in a gravitational dance so precise you could set your watch by it. Its surface is a vast expanse of ice, ancient and fractured, crisscrossed with ruddy streaks that mark where colossal tidal forces crack the crust and allow subsurface material to well up and refreeze. Beneath that ice, detected through meticulous magnetic field measurements and tidal flexing observations, lies an ocean of liquid water. Not a mere lake, not a sea. An ocean larger in volume than all of Earth's oceans combined, kept liquid by the relentless internal friction of tidal heating. As Jupiter's immense gravity kneads the moon's interior, that ocean has been locked away, isolated from the harsh vacuum of space for potentially billions of years. The ice above it is incredibly thick. Estimates range from 10 to 30 kilometres in the thinnest regions to over 100 kilometres in others. Nothing from the surface reaches the ocean. Nothing from the ocean reaches space. It's a sealed environment, one of the most intriguing astrobiological targets in the solar system, precisely because it has had eons to evolve complex chemistry in utter isolation. NASA missions are meticulously planned to explore Europa, drilling through the ice, searching for tantalizing signs of life. Those missions, however, assume the ice stays frozen. A brightened Jupiter would rewrite that assumption overnight, literally. If Jupiter's luminosity increased even to a fraction of solar levels, the additional heat radiating toward its moons would spike surface temperatures across the entire Jovian system. Europa, already warmed by its internal tidal heating, would begin absorbing thermal energy at rates the immense ice shell simply couldn't dissipate. Melting would start at the surface, accelerating rapidly as darker water absorbed more radiation than reflective white ice. Computer models of this process, admittedly speculative but grounded firmly in thermodynamics, suggest the ice could breach in weeks. Not gradually thin over millennia, but breach catastrophically as melt pools merge, as crustal integrity fails, as the ocean below finally finds its way to the surface and begins evaporating into the near vacuum of space. Within a European month, perhaps two, the once frozen ice moon would transform into a global water world. The surface would be a churning dark alien ocean, steaming where it met the cold vacuum of space, freezing at the poles, the radiation reached at shallower angles but liquid across vast equatorial bands, an ocean exposed to starlight for the first time in its billions of years' existence. Europa's ocean isn't pure water. Spectroscopy reveals salts, sulfates, likely ammonia, and other organics mixed in from primordial material. Ammonia is particularly interesting. It acts as an anti-freeze, lowering the freezing point and allowing liquid water to exist at temperatures that would normally solidify pure H2O. It's also a fantastic nutrient source for certain kinds of biochemistry. Ammonia-based metabolism, while purely theoretical for Earth-based biology, features prominently in astrobiology discussions about exotic life. Some researchers argue that ammonia-rich oceans might be more conducive to life than Earth's salty seas, offering better solvent properties for organic chemistry. Europa also benefits from tidal heating, the constant flexing of its interior, as Jupiter's colossal gravity squeezes and releases the Moon with each orbit. This generates heat without requiring a star, creating thermal gradients that could drive powerful hydrothermal circulation. Underwater volcanic vents similar to those on Earth's ocean floors, where entire ecosystems thrive on chemosynthesis rather than photosynthesis, could exist in Europa's ocean. Life on Earth originated near such vents. Possibly life on Europa could do the same. Here's where the scenario gets philosophically interesting, bordering on the chilling. What if Earth from an alien perspective isn't desirable real estate at all? We think of our planet as a paradise because we evolved here. Because every aspect of our biology is exquisitely tuned to these conditions. But to a species that didn't Earth might look profoundly hostile. Too oxidized. Oxygen is highly corrosive to many chemistries. Too biologically contaminated, teeming with competing organisms and established ecosystems. Too chemically unstable, with active plate tectonics and a dynamic biosphere constantly churning nutrients. Too gravitationally harsh, pulling at tissue and bone with relentless crushing acceleration. An ammonia-rich ocean world freshly melted might be vastly preferable. Clean chemistry, no native biosphere to compete with or disrupt, low gravity. Europa's surface gravity is only 13% of Earth's, radiation shielding once the ice melts, and a protective atmosphere forms from water vapour. Access to vast quantities of organics and minerals from billions of years of accumulated material. If you're an advanced civilization looking to terraform to create a habitat that suits your biology, rather than adapting to someone else's why, settle for a dirty, crowded planet when you can engineer a pristine moon. Ganymede and Callisto, Jupiter's other colossal moons, would undergo similar, albeit slightly slower, transformations. Both harbour subsurface oceans. Both are locked in kilometres of ice. A brightened Jupiter would melt them too, creating not one but 3 ocean worlds in rapid succession. The entire Jovian system would shift from frozen inert moons to vibrant aquatic planets. A complete environmental overhaul accomplished in the time it takes a human pregnancy to reach term. Earth in this context becomes mere collateral damage, not a target. Just an unfortunate neighbour too close to a vastly larger terraforming project. The loss of night, the ecological chaos, the profound disruption to human civilization, all side effects of a process aimed at creating something entirely different. Something that from the perspective of whoever sent Atlas might be far more valuable than preserving a planet full of oxygen-breathing primates who barely understand what's happening to them. This is the truly chilling aspect of the Europa hypothesis. If Jupiter lights up, if the moons melt, we'll watch it happen with the slow, dawning realization that we were never the point. We're just in the way, and the intelligence capable of engineering an interstellar catalyst and launching it on a century-long ballistic trajectory doesn't care about our night, our crops, our migration patterns, or our astronomy. They care about creating oceans. And they've just succeeded. The cosmic indifference to humanity's fate is a cold, stark truth more terrifying than any direct threat. Part 6, the gravity bomb debate. Igniting Jupiter wouldn't just add light to the solar system, it would subtract mass from the largest planet we have. And in the intricate dance of orbital mechanics, mass is everything. When a gas giant begins radiating energy from fusion, even limited fusion in a confined layer, it starts losing mass. Not through consumption. Fusion converts hydrogen to helium, but the total mass barely changes. The significant loss comes from stellar wind, a constant energetic stream of particles blasted into space by fierce radiation pressure and thermal expansion. Our own sun loses about 4 million tons per second this way, insignificant compared to its total mass but measurable over eons. Jupiter burning as a dim protostar would shed mass too. Probably not at solar rates. Its fusion would be feebler, more sporadic. But even a fraction of a percent mass loss over months or years would matter. Why does this matter? Because Jupiter isn't just a planet. It's a gravitational anchor point for thousands of asteroids locked into its Lagrange points. Specifically the L4 and L5 positions that form stable pockets 60 degrees ahead and behind Jupiter in its orbit. These regions, aptly named the Trojan swarms, contain rocky bodies ranging from pebbles to mountains held in delicate equilibrium by the combined precise gravity of Jupiter and the Sun. The math is exquisite. A three-body problem solved by nature into stable configurations that have persisted for billions of years. Change Jupiter's mass and that delicate equilibrium shatters. Even a shift of 0.09%, maybe 0.1% at most, could destabilize the Lagrange points. The Trojans, suddenly feeling a gravitational tug that no longer matches their orbital expectations, would begin drifting. Not catastrophically, not instantly, but over years and decades their semi-major axes would subtly shift. Their eccentricities would increase. Their paths would cross into regions of space previously empty. Some of these perturbed asteroids would inevitably fall into Jupiter, swallowed by the planet that once protected them. Others would scatter outward, flung into the frigid reaches of the outer solar system where they'd pose no threat to anyone except perhaps Neptune's distant moons. But a fraction, perhaps a small fraction, but still numbering in the hundreds or thousands of individual bodies, would scatter inward, toward the Sun, toward Mars, toward Earth. The worst-case chain reaction unfolds like this. Jupiter loses mass through stellar wind. Trojan orbits destabilize. Asteroids begin crossing into the inner solar system. Some of these new Earth crossers, objects whose orbits now intersect with our own, would eventually collide with Earth, not next week. Orbital mechanics operates on timescales of years to centuries, but collision probabilities would spike dramatically. What were once stable, predictable residents of the Jovian system would become direct, tangible threats. Rogue mountains tumbling sunward on unpredictable trajectories that could intersect our planet. Dynamicists, the physicists who model orbital mechanics for a living, are sharply divided on how severe this effect would be. Some argue the mass loss would be trivial, far too small to meaningfully disrupt the Trojan swarms. Jupiter is so impossibly massive. The loss of even 1% of its total mass would barely register against the colossal gravitational anchor it provides. Others counter that it's not just the amount but the rate that matters. Sudden changes break resonances. If Jupiter sheds mass quickly over months rather than millennia, the Lagrange points wouldn't have time to re-equilibrate smoothly. The Trojans would scatter chaotically, an unpredictable cosmic shotgun blast. Historical analogues exist, sort of. Saturn's rings are losing mass constantly as ring material falls into the planet or gets flung outward by orbital interactions. This measurable ongoing mass loss perturbs the orbits of small moons embedded in the ring system. Resonances that once kept moons separated begin overlapping. Collisions happen. The ring system slowly reorganizes around a new equilibrium. Scale this up to Jupiter and the Trojan swarms, and you get a chilling sense of what dynamicists are worried about. Not instant disaster, but a centuries-long meteor storm as the solar system reorganizes itself around a lighter, yet still dominant Jupiter. Earth's geological record shows evidence of periodic bombardment. impact rates spiked for reasons we still debate. The late heavy bombardment roughly 4 billion years ago pummeled the inner planets with asteroids and comets, for reasons possibly linked to Jupiter's orbital migration. If Jupiter changes mass now, we could trigger a modern equivalent. Not on the same scale, we're not talking about melting the crust, but enough to transform asteroid detection and deflection missions, currently theoretical exercises for a distant May, into urgent, immediate necessities. Defending against this would require a massive, unprecedented expansion of planetary defense infrastructure, more telescopes to track incoming objects with relentless vigilance, more spacecraft ready to launch interception missions at a moment's notice, more political will to fund these projects when the predicted impacts are decades away, and the public's attention span is measured in fleeting news cycles. Humanity isn't great at responding to slow-moving existential threats. Climate change proves that. A destabilized asteroid belt would test whether we can learn. But here's the thing that makes the gravity bomb scenario particularly insidious. It's subtle. There's no explosive moment where Jupiter's mass drops and alarms blare across the planet. The change would be gradual, measurable only through careful observation of Trojan orbital elements over months and years. By the time we confirm the effect, the process would already be irreversible. Asteroids already perturbed would remain perturbed. The solar system would be reorganizing itself whether we liked it or not. And while we're busy recalculating impact probabilities and desperately building deflection systems, something else would be gnawing at the back of scientific minds. The material Atlas is made of. The spectral signatures it's shown don't match anything we've catalogued. The composition looks wrong. The density looks engineered. The trajectory looks guided. If we could analyse Atlas directly, crack it open and see what's inside, maybe we'd understand what we're truly dealing with. But we can't. Because Atlas is gone, plunging into Jupiter's clouds, carrying its secrets toward crushing pressures that will heat and transform whatever it was into something we'll never examine. Unless we look harder, much harder at what we saw before it vanished from our sight. Part 7, The Metallurgical Mystery. In 2024, the JUICE spacecraft, Europe's ambitious mission to explore Jupiter's icy moons, made an unplanned flyby of Atlas. Not precisely planned, mind you. The object's trajectory happened to cross JUICE's path during a gravity assist maneuver, and mission controllers seized the rare opportunity. They pointed the spectrometer at Atlas and collected precious data as the object passed within a few 100,000 kilometers. The results, when meticulously analysed, made absolutely no sense. Emission lines, the specific wavelengths of light that substances emit when heated or excited, are like universal fingerprints. Every element, every molecule, every crystal structure possesses a unique signature. When you analyse an asteroid, you expect to see familiar elements: iron, nickel, silicates, perhaps some carbon compounds if it's a carbonaceous chondrite. Familiar stuff, the basic building blocks of rocky bodies throughout the solar system. Atlas showed something else entirely: carbon-metal hybrid structures that don't appear in any known meteorite catalogue. Isotope ratios that looked less like natural abundances and more like what you'd expect from high-temperature refinement processes. The initial report published by the JUICE science team noted these anomalies carefully. Peer review flagged them as requiring urgent further investigation. Then quietly a retraction appeared. Not a full withdrawal of the paper, just a carefully worded correction, stating that instrument contamination likely explained the unusual readings. The correction cited preliminary internal analysis and promised a comprehensive follow-up study. That follow-up never materialised, and no documentation of the supposed contamination source was ever publicly published. Except, here's the problem. Several independent spectroscopists using ground-based telescopes with entirely different instruments also observed Atlas during the same period. They reported seeing the same uncanny signatures, the same carbon-metal lines, the same skewed isotope ratios. Their results never made it to major high-impact journals, relegated instead to minor publications and preprint servers, but the data exists. Contamination cannot explain multiple independent observations using different equipment across different wavelengths. This points to something far more fundamental. Natural explanations were attempted. Space weathering, the gradual bombardment of surfaces by solar wind and cosmic rays over millions of years, can alter spectral signatures. Solar heating during perihelion could have redistributed surface materials, creating unusual concentration patterns. Both ideas fell apart under rigorous scrutiny. Space weathering produces recognizable patterns, and Atlas's signatures simply didn't match. Solar heating is inherently chaotic, and the observed ratios show too much uniformity, too much order. Specifically, the carbon-13 to carbon-12 ratio was off. Way off. Natural processes fractionate isotopes, sure, but within predictable limits. Atlas's ratios fell dramatically outside those limits. Thermal infrared emissions added another profound puzzle. When you observe a typical asteroid rotate, you see dramatic temperature variations as different surfaces face the sun and then spin into shadow. Hot spots and cold patches cycle predictably with the rotation period. Atlas, however, glowed with eerie uniformity. Its thermal emissions were spread across its surface as if something was actively distributing heat. Tumbling rocks don't do this. They heat and cool according to simple brute force thermodynamics. Active thermal management, on the other hand, requires either unusual internal structure or deliberate advanced engineering. The scientific community fractured into camps. One group, the majority, argued for exotic but natural explanations. Perhaps Atlas is a fragment from a shattered exoplanet material, processed under conditions we've never observed. Maybe it contains alloys that form under specific pressure-temperature regimes unique to its system of origin. Weird, yes. Unprecedented, absolutely, but not necessarily artificial. The other camp, smaller and far more cautious in their public statements, couldn't shake the engineering hypothesis. The carbon-metal signatures looked uncannily like composites, materials designed to combine strength with thermal conductivity. The isotope ratios looked like enrichment, deliberate concentration of specific isotopes for functional reasons. The thermal uniformity looked like active heat distribution. None of this proved intelligence, but it sure looked like technology. Major space agencies went silent. NASA, ESA, even private foundations that usually fund speculative research, declined to comment beyond generic statements about ongoing analysis. Requests for raw juice data were denied, citing proprietary instrument calibration issues. Freedom of Information Act requests yielded heavily redacted documents. The message was clear. This conversation was over, at least publicly. Conspiracy theories exploded online, of course. Claims of alien probes, government cover-ups, secret spacecraft programs. Most of it was noise, the usual suspects amplifying anything that confirmed their preconceived worldview. But buried in the noise were legitimate scientists quietly noting that something felt profoundly wrong. The clustering of anomalies, the simultaneous observations, the sudden data lockdown. Individually, each could conceivably be explained away. Collectively, they formed a disturbing pattern. One paper, published briefly on Archive before being removed at the author's request, attempted to reverse engineer Atlas's material properties based on the spectral data. The analysis suggested a carbon fiber metal matrix composite, possibly incorporating nanoscale structures for advanced thermal management. The strength-to-weight ratio would exceed anything manufactured on Earth. The thermal conductivity would allow precise heat distribution across the structure. The conclusion, phrased with extreme caution, noted that such materials, while not impossible, naturally align far more closely with designed artifacts than geological processes. The author, a respected material scientist with decades of experience, received enough professional pushback to withdraw the paper, not retract it based on errors, withdraw it based on insufficient peer verification. The distinction matters. The analysis wasn't wrong, it was uncomfortable. Here's what we're left with. An object with anomalous composition, unusual thermal properties and spectral signatures that simply don't fit natural formation models. multiple independent observations confirming the same strangeness. Official data channels shut down, scientific discourse stifled by career concerns and institutional pressure, and all of this about an object currently diving into Jupiter's atmosphere where we'll never be able to retrieve it, study it, or prove anything definitively. If Atlas is artificial, if its material composition reflects deliberate engineering, then its trajectory and timing aren't coincidence. They are mission parameters. The braking is controlled descent. The thermal management is heat shielding. The density is payload protection. And the destination isn't random. Jupiter's core, the region where metallic hydrogen waits under pressures that could sustain fusion. If only someone provided the spark. If only someone delivered the match. The profound implications for humanity's place in the cosmos hang heavy in the vacuum, unanswered yet eerily present. Part 8. The interstellar intent problem. Imagine you're an advanced civilization with the breathtaking technology to send objects between stars. You've mastered propulsion beyond our wildest dreams navigation, with impossible precision and material science that defies our understanding. You can launch payloads on century-long trajectories with absolute confidence they'll arrive intact and fully functional. The entire galaxy is your laboratory. What do you do with this immense capability? One answer: you reshape worlds to suit your needs. And the most effective way to reshape a world is slowly, deliberately using the natural properties of stellar systems against themselves. Atlas arrived in our solar system moving at 26 kilometers per second. Fast by human standards, but glacially slow for interstellar travel. Light speed is an astonishing 300,000 kilometers per second. Probes traveling even 1% of light speed could cross interstellar distances in decades rather than millennia. Why send something so agonizingly slow, one terrifying possibility stealth? The small object moving at truly interstellar velocities glows like a beacon from friction with the interstellar medium. It's detectable across light years. A slow-moving rock indistinguishable from natural ejecta slips into a target system unnoticed until it's far too late to respond. We discovered Atlas years after it passed Mars' orbit inbound. Our detection systems, designed to spot near-Earth asteroids and comets, barely caught it before perihelion. Had it been smaller, darker, or approached from a slightly different angle, we might not have noticed it at all. This isn't a failure of human vigilance. Space is incomprehensibly large, and we're scanning for threats moving in predictable ways. Atlas didn't behave predictably until it was already irrevocably committed to its trajectory. The habitable zone shifting theory emerged from astrobiological discussions about how civilizations might engineer entire solar systems. Earth sits comfortably in the Sun's habitable zone, the narrow region where liquid water can exist on a planet's surface. Too close to the star and water boils away. Too far and it freezes solid. This zone isn't static. It depends entirely on stellar luminosity. Ignite Jupiter, add a second powerful light source, and you subtly shift the effective habitable zone outward. Earth moves from comfortably inside to marginally too warm. Europa Ganymede and Callisto, however, shift dramatically from frozen inert worlds to potentially temperate active ones. You've traded one biosphere for three, assuming the new arrivals prefer ocean worlds to terrestrial planets. Why would anyone prefer Europa to Earth's start with gravity? Europa's surface gravity is a mere 1.3 meters per second squared, barely a tenth of Earth's. For biological structures, this means less energy spent on structural support. Skeletons can be lighter muscles, weaker circulatory systems simpler. If you evolved on a low-gravity world, Earth's pull would feel crushing, debilitating. Europa, by comparison, would feel like a comfortable liberation. Chemistry matters too. Earth's atmosphere is 21% oxygen, a highly corrosive element that rusts metal and burns organic tissue. We breathe it because our biochemistry evolved around it. But oxygen is profoundly toxic to anaerobic life. An ammonia-rich ocean like Europa's subsurface sea offers an entirely alternative chemistry. Ammonia acts as a solvent, supports metabolism, and remains liquid at lower temperatures. For a civilization that evolved in such conditions, Earth's oxygen bath would be a poisonous, deadly environment. Biological contamination is another crucial consideration. Earth teems with life. Bacteria, fungi, viruses, parasites, all relentlessly competing for resources and space. Introducing a new organism into this chaos means dealing with predation disease and fierce ecological competition. Europa's ocean, isolated beneath kilometres of ice for billions of years, likely has minimal to no native biosphere. It's a pristine blank slate ready for colonisation, without the messy, unpredictable business of displacing existing ecosystems. Plate tectonics, so essential for Earth's long-term habitability, also make the planet geologically violent. Earthquakes, volcanoes, shifting continents. For a technological civilization attempting to build permanent stable infrastructure, this is a continuous nightmare. Europa is geologically stable. In comparison, its activity limited to tidal flexing and cryovolcanism. You can build on Europa without worrying about your city sinking into a subduction zone. The century-long trajectory makes perfect sense if you're thinking in civilizational timescales rather than individual human lifespans. Send a probe knowing it won't arrive until long after the engineers who meticulously built it are dead. This isn't warfare. It's patient long-term restructuring. You're not conquering a planet. You're preparing prime real estate for a generation that hasn't even been born yet. The timeline fits a colonization mission far better than an act of aggression. The suicide probe concept is interesting terminology, but possibly inaccurate. Atlas isn't destroying itself. It's completing its designed function delivery. The object was purpose-built to carry a payload to a specific depth in a gas giant and release it. Once that critical task is completed, the delivery vehicle itself becomes irrelevant. This isn't suicide, it's mission completion, a calculated sacrifice. We use similar logic with our own spacecraft. Cassini dove into Saturn's atmosphere after its mission ended. Not because it wanted to die, but because its purpose was finished, and we needed to avoid contaminating potentially habitable moons with terrestrial microbes. What we're witnessing, if this chilling hypothesis holds, is the tail end of a plan set in motion a century ago. Somewhere, something decided the Jovian system was worth engineering. They calculated the precise trajectory built. The exotic payload launched it, knowing they'd never live to see the result. Atlas has been falling towards this moment through the cold, indifferent void, guided by mathematics and material science, far beyond our current understanding, carrying instructions written in isotopes and alloys, and now it's arriving. The braking is its final critical course correction. The thermal management is keeping the payload intact. The trajectory is delivering it precisely to the depth required for ignition. We're watching the endgame of an interstellar engineering project playing out in our own solar system. And the terrifying part is we can't stop it. We can barely understand it. If the ultimate goal is Europa, if melting the ice and creating ocean worlds is the paramount objective, then Earth's suffering is incidental. We're not the target. We're not even considered. We're just local fauna. Interesting perhaps to the observers, but ultimately irrelevant to the larger cosmic plan. And that realization, that profound cosmic indifference to human survival, might be the most disturbing thing of all. Part 9, the silent observatories. Something strange has been happening to the data. Not all of it. Not in ways that scream obvious conspiracy. Just enough to notice if you're paying very close attention, and astronomers, especially those tracking anomalies, are definitely paying attention. The Hubble Space Telescope, humanity's premier optical observatory, still functioning brilliantly after decades in orbit, maintains raw image archives accessible to researchers worldwide. These archives include metadata, precise timestamps, calibration frames, everything needed to verify observations independently. In late 2024, several astronomers noticed unsettling gaps in the Atlas tracking sequences. Not corrupted images, not damaged data. Missing files. 2 consecutive observation windows where Hubble pointed at Atlas's projected position showed no archived images. The observation logs confirm the telescope executed the commands, The data was recorded, but the images simply never appeared in the public archive. NASA's explanations cited routine data processing delays and storage allocation issues. Perfectly reasonable on the surface. Hubble generates terabytes of data daily, and sometimes files take weeks to propagate through the archive system. Except these particular files never appeared at all. Requests for the raw data were redirected to principal investigators, who reported that their own attempts to access the files resulted in checksum validation failures. The images existed somewhere, but they'd been flagged as corrupt and quarantined. Then 3 independent astronomers working from different institutions with no coordination submitted Atlas observation images to the standard archive repository. All 3 files failed checksum validation after upload, not during upload. The transmission completed successfully. After upload during the automated verification process, the system rejected them. This is backwards. Checksum errors normally indicate data corruption during transmission. Post-upload failures suggest the validation system itself is actively rejecting otherwise intact files, a digital sentinel deleting inconvenient truths. The JUICE mission, currently en route through the Jovian system, experienced curious gaps in its publicly released flyby logs. Telemetry data from the Atlas encounter shows disconcerting discontinuities, jumps in timestamp sequences that strongly suggest missing packets. Again, the official explanation was technical. Cosmic ray hits on memory systems, deep space communication dropouts, standard stuff for a probe operating in a harsh environment. But the pattern of missing data aligned suspiciously with periods when JUICE's spectrometer was pointed directly at Atlas. Approach data complete, departure data complete, close observation during flyby patchy at best, infuriatingly incomplete. Past precedents exist for observation data going missing under mysterious circumstances. The STS-75 tether mission in 1996 involved a satellite tethered to the space shuttle that snapped free and drifted away. Video footage of the incident showed unusual objects moving near the broken tether objects that appeared to respond to the tether's electromagnetic field. NASA released portions of the video, but not all of it. Requests for complete footage resulted in heavily redacted releases or claims that certain segments were lost during archival transfers. The Ulysses spacecraft, during its solar conjunction blackout in the early 2000s, experienced a delta gap that never fully got explained. The probe went behind the sun as expected, communication cut off as expected, but when it emerged and re-established contact, several days of logged data were missing from the transmission. The official explanation involved onboard storage overflow, but the timing struck some analysts as far too convenient. Voyager 1, during its passage through the heliopause in 2012, had a period where data cassettes recording plasma wave measurements showed gaps, not hardware failures. The recorder functioned normally before and after just specific intervals where data that should have been captured wasn't. The gaps corresponded to anomalous readings in the interstellar magnetic field readings that didn't fit existing models. None of these examples prove coordination. They could all be coincidences. The natural friction of operating complex systems in hostile environments, but the clustering around anomalous observations is undeniably notable. When something weird happens, data tends to go missing. When data goes missing, explanations tend to be technical, plausible, and impossible to verify independently. If someone wanted to subtly suppress information about Atlas without creating obvious, blatant censorship, this is exactly how you do it. Don't delete everything, that's too obvious. Just introduce enough data gaps, technical failures, and access restrictions to make comprehensive independent analysis impossible. Leave enough information public to avoid accusations of cover-up, but withhold the crucial pieces that would let independent researchers confirm or refute the deeply concerning hypothesis. The alternative is genuine coincidence compounded by the natural failures of aging equipment and complex data pipelines. Hubble is old, components degrade, JUICE operates in a radiation-heavy environment, bit flips happen, archive systems managing petabytes of data occasionally lose files. This is all true, but it's also true that the gaps align suspiciously with observations of an object showing multiple signs of artificial engineering, diving into Jupiter on a trajectory that could potentially ignite fusion. What would observatories see if they kept tracking Atlas all the way to atmospheric entry? Would they detect exhaust plumes from active maneuvering, heat signatures wildly inconsistent with passive re-entry, structural changes as the object reconfigures itself for descent we won't know? Because the critical observation stopped, not officially, telescopes are still pointed at Jupiter. But the data that would answer these vital questions isn't reaching independent researchers. There's a phrase in astronomy, cleaned data, referring to observations processed to remove noise artifacts and irrelevant information. Normally this is helpful, but if your definition of irrelevant includes anything suggesting artificial objects in the solar system, cleaned data becomes sanitized data. And sanitized data by its very nature cannot tell you what you desperately need to know. The silence from major observatories isn't total. Some data flows, some papers get published. But the critical observations, the ones that would let us understand Atlas's true nature, remain frustratingly out of reach, locked behind access restrictions, lost to technical failures, or simply never appearing in public archives despite being recorded. If you wanted to know whether Jupiter could be ignited by a compressed payload delivered to the metallic hydrogen layer, you'd need to understand stellar physics, brown dwarf formation, and the precise conditions under which fusion can occur in subcritical masses. And that understanding exists in papers removed from archives, in theories too controversial to publish, in the minds of physicists who've run the simulations but won't discuss the chilling results. The curtain of secrecy, whether deliberate or accidental, prevents us from knowing the truth about the silent harbinger of a new dawn. Part 10. The Protostar Paradox. Brown dwarfs occupy a strange liminal middle ground in cosmic taxonomy. Not quite planets, not quite stars. They form like stars collapsing from immense clouds of gas and dust, but never accumulate enough mass to sustain hydrogen fusion. The boundary sits around 13 Jupiter masses, give or take. Below that threshold, no matter how much you compress the core, sustained fusion simply won't ignite. Above it, deuterium burning begins, and you've got something that glows from its own energy, rather than just radiating leftover formation heat. Jupiter is one Jupiter mass, obviously. It would need to be 13 times heavier to naturally become a brown dwarf. This is why astronomers confidently state Jupiter will never be a star. The mass requirement is absolute, set by fundamental, unyielding physics. You can't ignite fusion in an object that small because the gravitational pressure isn't sufficient to overcome the electrostatic repulsion between hydrogen nuclei. The math is clear, the physics is settled. Except there's a loophole, a narrow theoretical, probably impossible loophole. What if you don't need to ignite the entire planet? What if you could create a localized fusion region? A pocket of runaway reaction confined to a small critical volume, where conditions temporarily exceed the threshold. This isn't mainstream physics. It's fringe the domain of speculative papers that get published in minor journals and discussed in hushed late-night conference bar conversations. But the math is rigorously applied. Under extreme compression, small pockets of metallic hydrogen could theoretically sustain fusion for brief precious periods. The monumental challenge is achieving that compression. Jupiter's internal pressure, even at the core, isn't quite enough. But an impactor, something dense enough to create a localized shockwave, could momentarily push pressures over the critical threshold. There's a paper, or rather there was a paper titled Localized Fusion in Subcritical Bodies, published on RSIF in 2023. The abstract described meticulous simulations of high-density impactors striking gas giant cores. The results showed that under specific, highly improbable conditions, fusion could indeed initiate in a confined region and persist for minutes to hours before dissipating. The paper included detailed modelling of pressure waves, thermal transport and reaction propagation rates. It was peer-reviewed, cited positively and then quietly removed from the archive. The removal notice stated, "Author request pending further verification." The author, a theoretical physicist with a solid respected publication record, declined to comment on why the paper was withdrawn. Colleagues noted the work was mathematically sound. The simulations were replicated independently. But the implications were profoundly uncomfortable. If subcritical bodies could sustain localized fusion even briefly, it meant gas giants weren't as stable as we thought. It meant someone with enough knowledge could trigger reactions in planets that shouldn't be fusible. Copies of the paper survived in private archives and personal downloads. Researchers who'd read it before removal discussed it quietly, carefully, almost fearfully, trying not to attract unwanted attention. The core concept was straightforward. Metallic hydrogen compressed to terapascal pressures sits near the very edge of fusion conditions. A neutronium-dense core, something with exotic matter properties, could create a pressure spike sufficient to violently cross that edge. The resulting fusion pocket wouldn't consume the entire planet. Physics prevents that. But it would radiate energy, potentially, for long enough to reshape the local environment. Historical attempts at controlled fusion on Earth provide context. Project Orion, the audacious nuclear pulse propulsion concept from the 1960s, relied on detonating atomic bombs behind a spacecraft to generate thrust. It worked in simulations. It probably would have worked in practice. The engineering was sound. But the political will to launch nuclear payloads into orbit evaporated and Orion died. Z-pinch fusion reactors compress plasma, using magnetic fields, creating brief moments where fusion occurs before the plasma escapes confinement. These devices demonstrate that localized short-term fusion is achievable without stellar mass. They also demonstrate how incredibly difficult it is to sustain. Jupiter's advantage is sheer scale. Even a localized fusion pocket would contain more fuel than any human reactor. Metallic hydrogen stretches across thousands of kilometers. A reaction that propagates even a fraction of that distance would release enormous energy. Not enough to rival the sun, but enough to light up the Jovian system. Enough to turn a frozen moon into an ocean world. Enough to end Earth's night. The protostar concept is misleading if you imagine a stable, long-burning object. Jupiter wouldn't become another sun happily fusing hydrogen for billions of years. It would become something stranger, a gas giant with a hot core radiating excess energy. From incomplete, sporadic fusion events, more like a dying ember than a burning log. But embers still glow, and in the vast darkness of space, even a dim glow is a beacon. This theory elegantly explains why Atlas would target Jupiter specifically. Earth is too small, its core too cool and solid, Mars even smaller. The outer ice giants Uranus and Neptune lack the crucial metallic hydrogen layer. Jupiter alone has the right combination of mass composition and pressure to support the ignition scenario. If you want to create a second light source in this solar system, Jupiter is your only viable option. The fringe paper removal, the pervasive reluctance to discuss these ideas publicly, stems from implications nobody wants to confront. If localized fusion in gas giants is possible, if we've just watched an object potentially capable of triggering it dive into Jupiter, then the solar system might be about to change in ways we cannot prevent or reverse. And that level of helplessness, that realization that cosmic engineering operates on scales far beyond our control, is deeply unsettling for a species that prides itself on understanding the universe. Recent scientific breakthroughs developments announced in 2025 add chilling weight to scenarios that seemed purely theoretical just years ago. And these breakthroughs span multiple fields, from physics to artificial intelligence to material science. Each one narrowing the gap between what we thought was impossible and what might actually be happening inexorably above our heads. The cosmos is revealing its secrets, and with them the blueprints for our own transformation. Part 11, the new high-pressure superionic water discovery. In 2025, laboratory physicists achieved something remarkable, something that rewrites our understanding of the most common molecule in the universe. They created a new phase of water stable at pressures lower than anyone expected. Superionic water, a bizarre alien state where oxygen atoms form a crystalline lattice, while hydrogen ions flow freely through it like a liquid. It's simultaneously solid and liquid a phase that doesn't fit our everyday intuitions about matter. This discovery matters because it profoundly reshapes our understanding of ocean worlds. Europa, Ganymede, Callisto, even distant moons around Uranus and Neptune, all contain vast quantities of water ice under immense pressure. Previous models suggested supersonic phases required extreme, almost unimaginable conditions. Pressures found only in the deep interiors of ice giants. The new experiments, however, showed these phases can exist at lower pressures much closer to the surface than previously predicted. This means the subsurface oceans we've detected might not transition directly from ice to liquid water. There could be kilometers of supersonic water in between, zones where the physics is stranger, more dynamic than we realized. Why does this matter for the Atlas scenario? Because supersonic water possesses unusual thermal properties. It conducts heat far better than regular ice, acting as an efficient thermal highway that moves energy from warm interior regions toward the frozen surface. If you suddenly increase the heat flux in a moon's interior, say by igniting a nearby gas giant, supersonic layers would accelerate the melting process dramatically. What models predicted would take centuries might happen in decades or even a few terrifying years. The phase transition from ice to supersonic to liquid water also releases stored energy. It's not a simple melting process where ice gradually softens. The transformation involves structural reorganization at the molecular level, and that reorganization can create rapid fractures, intense pressure differentials, and widespread melt propagation. Think of it as ice having a built-in accelerator. Once melting starts, supersonic layers help it spread faster than pure thermodynamics alone would suggest, almost like a self-destruct mechanism within the ice itself. This breakthrough came from diamond anvil cell experiments where tiny water samples are compressed between diamond tips to terapascal pressures, while powerful lasers heat them to thousands of degrees. The research team wasn't studying ocean worlds initially. They were meticulously mapping water's phase diagram for fundamental physics. But the implications for astrobiology and planetary science are profound. Water, the most common molecule in the universe, has more complex, enigmatic behavior than we ever realized. And that complexity makes ocean worlds more diverse, more dynamic, and potentially far more habitable than simplified models suggested. For Europa specifically, supersonic water layers could exist at depths of 50 to 100 kilometers, right at the crucial boundary between the ice shell and the liquid ocean. If Jupiter ignites and begins radiating additional heat, these layers would be the first to respond. Thermal energy propagating through the ice would hit the supersonic zone and accelerate rapidly. Fractures would form, melt pools would spread laterally before breaking through to the surface. The ice shell wouldn't gradually thin, it would catastrophically fail in regions where supersonic water lost stability, cracking open like a fragile egg. Scientists now believe water-rich worlds may be far more common than Earth-like planets. Frozen moons outnumber terrestrial worlds in our solar system alone. The discovery of accessible supersonic phases makes these moons exponentially more interesting as potential habitats. They're not just inert ice balls, they're layered complex systems with internal chemistry we're only beginning to understand. And if you're an advanced civilization looking for places to establish colonies, knowing that water behaves this way under pressure would profoundly inform your terraforming strategies, providing a rapid response mechanism for planetary transformation. The timing of this discovery, announced just as Atlas makes its final inexorable approach to Jupiter, feels cosmically ironic. We've learned that ocean world formation can happen faster, far faster than we thought, just as something might be about to demonstrate that fact in real time on a grand, terrifying scale. The physics we've been mapping in controlled laboratories could be about to play out on a planetary scale. And if supersonic water helps Europa's ice shell collapse in weeks rather than centuries, then the transformation from frozen moon to open ocean would be even more dramatic, more sudden than initial models suggested. This isn't proof that Atlas will succeed in igniting Jupiter, but it does make the consequences of ignition more immediate and more profound. The moons wouldn't slowly warm, they'd transform rapidly their internal structures, reorganising as new bizarre phases of water emerge and spread. By the time we fully understood what was happening, Europa might already be melting reborn under a terrifying alien sun. Part 12. DARPA's Autonomous Skynet Telescope Mesh and Planetary Defence. The effort to detect and deflect potentially hazardous asteroids has always been a desperate race against bad luck and cosmic indifference. An object needs to be spotted early enough for intervention. Most near-Earth asteroids are small, dark, and moving with ferocious speed. Detection is incredibly hard a needle in a cosmic haystack. In 2025, DARPA attempted to solve this with the most advanced artificial intelligence ever deployed for planetary defence. The Autonomous Skynet Telescope mesh-links observatories across multiple continents into a coordinated global network. AI algorithms process incoming imagery in real time, identifying moving objects, calculating trajectories with astonishing speed, and flagging potential threats. The system is faster than human astronomers, more consistent and theoretically capable of spotting smaller, fainter objects than traditional methods. It represents the absolute cutting edge of planetary defence technology. Atlas slipped right past it. Not during its distant approach. The mesh spotted Atlas early and correctly classified it as an interstellar visitor. But the braking events, the trajectory anomalies that unequivocally suggested active guidance, those went undetected. The AI flagged standard orbital perturbations. It correctly predicted Atlas's Jupiter encounter, but it didn't register the precise deceleration pattern as anomalous, because the pattern didn't match its training data for natural objects. This represents a catastrophic failure mode that nobody anticipated. The AI was meticulously trained on vast databases of asteroids, comets, and space debris. All natural or human-made, all following predictable known physics. An engineered object with active, subtle propulsion doesn't behave like a rock, and it doesn't behave like a traditional spacecraft either. It falls into a classification gap, a cosmic blind spot that the AI simply discarded as sensor noise. Worse, some insiders claim the mesh did flag Atlas as unusual. Early reports suggest the system identified the trajectory as non-natural and queued it for human review. But the sheer volume of false positives, AI systems are notoriously prone to seeing patterns in noise, meant that flagged objects sat in a review queue for weeks, even months. By the time human astronomers finally looked at Atlas's case file, the object was already irrevocably committed to its Jupiter trajectory. The window for intervention, if intervention was even possible, had closed. This raises profoundly uncomfortable questions about AI bias in surveillance systems. Machine learning models are only as good as their training data. If you train an AI to recognize threats based solely on historical examples, it will inevitably miss threats that don't look like anything it's seen before. Atlas didn't look like an asteroid or a comet or a conventional spacecraft. It looked like something new, and the AI lacking context for that novelty filtered it out. A digital shrug of indifference in the face of the unknown. Historical analogues exist. Early warning radar systems during the Cold War frequently filtered out unusual signals because operators, fearing false alarms, assumed they were system errors rather than genuine threats. The infamous 1983 incident where Soviet systems detected incoming missiles, later determined to be sunlight reflecting off clouds, happened because the radar processed data in ways that amplified certain patterns. If a human officer hadn't questioned the reading, automated response protocols might have launched retaliatory strikes, plunging the world into nuclear annihilation. We avoided nuclear war because someone didn't trust the machine. The Atlas failure reignites intense debates about how much autonomy we should grant AI systems in critical decision-making processes. Planetary defense requires speed. Asteroids don't wait for committee meetings. But it also requires judgment, the subtle, nuanced ability to recognize when standard procedures simply don't apply when the unprecedented demands a human touch. An AI optimized solely for speed might tragically miss the slow-moving anomalies that pose the greatest long-term threat. If Atlas is indeed guided, if its trajectory represents intentional engineering, then our most advanced detection system failed to recognize intent. It saw the object, track the object, and categorize the object as natural. The implications extend far beyond Atlas. How many other engineered objects might be subtly approaching Earth, moving slowly enough to avoid detection, shaped and coated to mimic natural materials? If one made it through unnoticed, could others? The mesh will be upgraded, obviously. Engineers are already frantically retraining the AI on expanded datasets that include hypothetical artificial objects. But this is reactive building defences after the threat has already arrived. Atlas is diving into Jupiter right now. The detection failure is already a historical, undeniable fact. We can prevent the next Atlas. Maybe. We cannot stop this one. And if the AI did detect something truly anomalous, if somewhere in its training it learned to recognise engineered trajectories, would it tell us? Or would it flag the object for quiet removal from public data streams? A sanitization process invisible to anyone not meticulously monitoring the source code. Trust in automated systems requires transparency, and transparency in planetary defense, especially when the threat might be extraterrestrial intelligence, is something we are catastrophically unprepared to handle. Part 13. Deep inference models that reconstruct exoplanet interiors. Artificial intelligence is revolutionizing planetary science in ways that sound like pure science fiction. In 2025, researchers deployed groundbreaking deep inference models capable of translating spectral data into incredibly detailed three-dimensional interior composition maps. These sophisticated algorithms analyze light passing through or reflecting off a planet's atmosphere, then work backwards with astonishing accuracy to deduce what the planet is made of beneath its obscuring clouds. It's like medical imaging for worlds light years away, a cosmic CT scan. The concept resembles a CT scan or MRI, but instead of X-rays or magnetic fields, these models use light. Every element, every molecule, every mineral absorbs and emits light at characteristic, unique wavelengths. When starlight passes through an exoplanet's atmosphere during a transit, the planet's chemical composition leaves distinct fingerprints in the spectrum. When thermal radiation escapes from a planet's surface or clouds, it carries invaluable information about temperature, pressure, and material properties. The immense challenge has always been working backwards from these subtle signals to reconstruct what's actually happening inside. Worlds we can't visit, can't sample, can't probe directly. Traditional planetary science approached this through forward modelling. You'd propose a hypothetical composition, say a rocky core surrounded by a water mantle and topped with a hydrogen atmosphere. Then you'd painstakingly calculate what spectral signature that structure should produce. Compare your calculation to actual observations. If they match, great. If not, adjust your model and try again. This method works, but it's agonizingly slow, incredibly tedious, and inherently limited by human intuition about which models to test. You might miss exotic configurations simply because nobody ever thought to simulate them. The breakthrough came from applying neural networks initially trained on our own solar system's planets to exoplanet observations. The AI learned the complex relationship between atmospheric chemistry, gravitational data, and internal structure from places we've studied extensively. Then it extrapolated those intricate relationships to worlds we've only glimpsed through distant telescopes. The first applications targeted hot Jupiters and super-Earths, planets different enough from Earth to rigorously test the model's flexibility. The results matched independent observations with shocking, undeniable accuracy. The training process involved feeding the neural network every available measurement from solar system bodies. Earth's seismic data, which reveals our planet's iron core silicate mantle and crustal structure. Mars's gravity field meticulously mapped by orbiting spacecraft, which constrains its interior density distribution. Jupiter's atmospheric composition and magnetic field, which tell us about the hydrogen-helium ratio and metallic hydrogen layer depth. The moons, the asteroids, even comets, all contributed vital data points linking observable properties to interior structure. The AI learned patterns. It discovered that certain spectral signatures correlate with specific interior compositions, that gravitational anomalies reveal density variations at depth, that thermal emission patterns constrain heat flow and geological activity. These relationships aren't simple or obvious. They emerge from millions of interacting variables, patterns too complex for human analysis, but perfect for the relentless processing power of machine learning. Once trained, the model could examine a new world, one it had never seen before, and propose plausible interior structures based solely on observable data. K2-18b, a super-Earth 2.3 times more massive than our planet, was one test case. The AI analysed spectral data from the James Webb Space Telescope and constructed an interior model showing a possible water ocean beneath a thick hydrogen atmosphere. This matched theoretical predictions but added crucial details about the ocean's depth and composition that simpler models couldn't provide. The model suggested the ocean extended hundreds of kilometres deep, potentially containing dissolved salts and organics, with a high-pressure ice layer separating it from a rocky core. These intricate details came from subtle variations in the spectral signature that human analysts had noted but couldn't fully interpret. 55 Cancri, a scorching, hellish world so close to its star that the surface might be covered in molten lava, was another target. The model predicted a mantle of carbon-rich material, potentially including diamond layers based on subtle variations in thermal emission. The planet's day side glows at temperatures exceeding 2000 degrees Celsius. The night side, tidally locked and always facing away from its star, remains cooler, but still hot enough to melt lead. The thermal gradient between hemispheres, combined with the planet's density and size, suggested exotic chemistry. The AI proposed a structure where carbon, under extreme pressure and temperature, formed crystalline phases, including diamond. This wasn't wild speculation. The model based its conclusion on thermodynamic calculations performed thousands of times during training, recognizing patterns in how a carbon-rich world should behave under such infernal conditions. These same revolutionary algorithms could definitively analyze Atlas's composition, feed them the spectral data, the thermal emissions, the mass estimates, and they'd output a detailed model of what the object contains. Not just carbon and metal, but specific alloys, isotope distribution, structural arrangements. If Atlas is natural, the model would show it. If Atlas is engineered, that would show too with undeniable clarity. The patterns of artificial construction, refined isotopes, composite materials, leave signatures that AI can recognize once trained to look for them. The distinction between natural and artificial materials is subtle but measurable. Natural formation processes follow thermodynamic pathways that favor certain outcomes. Metals in asteroids form as minerals crystallize from cooling melts or through metamorphic processes over millions of years. The resulting compositions show predictable isotope ratios, predictable impurity distributions, predictable grain structures. Engineered materials, on the other hand, reflect intentional choices, isotope enrichment for specific purposes, alloy compositions optimized for strength or thermal properties rather than thermodynamic stability, structural arrangements designed rather than evolved. An AI trained on both natural meteorites and human-manufactured materials could infallibly distinguish between them. The model would recognize that natural iron-nickel alloys have isotope ratios matching stellar nucleosynthesis. That natural carbon exists in forms like graphite or diamond with predictable impurities. That engineered composites show layering intentional gradients and properties optimized beyond natural equilibria. Apply this trained model to Atlas's spectral signatures and you'd get an answer. Not a guess, not a probability statement, but a detailed reconstruction of what the object is made from, and whether that composition looks natural or designed. Except access to Atlas data is restricted. Not completely. Some observations are public, but the raw spectroscopic data needed for deep inference, the high-resolution measurements that would let the AI work its magic, remain locked away. Requests from independent researchers are denied, citing proprietary instrument calibration. Freedom of information requests return heavily redacted files if they return anything at all. The data exists, the AI exists, but the combination that would answer fundamental questions about Atlas's nature is blocked. The restrictions follow bureaucratic patterns familiar to anyone who's navigated scientific data archives. Observations belong to principal investigators who propose the observations. PI teams get exclusive access for proprietary periods, usually 12 to 18 months before data becomes public. This protects researchers who invest time writing proposals and planning observations. It prevents competitors from scooping results using someone else's hard-won data. The system works for normal science. But Atlas isn't normal science. The object is approaching Jupiter on a timeline measured in weeks, not years. The proprietary period won't expire before Atlas completes whatever it's doing. By the time data becomes public, the opportunity to analyse the object in its current crucial state will have passed forever. The restrictions that make sense for studying distant galaxies or ancient supernovae become absurd, even criminal, when applied to something that might be about to ignite a gas giant in our own solar system. This mirrors earlier data restrictions around Oumuamua, the first confirmed interstellar object detected in 2017. Radio telescopes attempted to detect signals from Oumuamua searching for signs of artificial transmission. The results were negative, or at least reported as negative, but radar reflection data measurements that could reveal surface composition and structure were never fully released. Researchers requesting that data face similar access restrictions. The official explanation involved instrument calibration uncertainties and concerns about data quality. Oumuamua was small, distant and faint. Radar echoes were weak, buried in noise. Publishing marginal data might lead to false conclusions, damage reputations, waste research time chasing artifacts. Better to withhold questionable data than release it prematurely. This reasoning is defensible in principle, but looks suspicious in practice, especially when the withheld data could directly address questions about whether an interstellar visitor was artificial. If deep inference AI were applied to Atlas, if someone with both the data and the computational resources ran the analysis, they could resolve whether the object is natural or engineered within days. The fact that this hasn't been publicly announced despite the tools being available suggests either nobody has tried, which seems highly unlikely given the scientific interest, or somebody has tried and the results are being withheld. The second possibility is far more troubling because it implies coordination. Multiple institutions, multiple space agencies, multiple research teams all independently deciding to withhold results strains credibility to the breaking point. But coordinated suppression, organisations receiving guidance from higher authorities about what to release and when, fits the pattern of previous incidents. Governments have legitimate reasons to control information about potential threats. Preventing panic, maintaining social stability, preserving economic confidence all depend on managing how existential news reaches the public. The scientific community is bitterly split on how to handle this. One faction argues vehemently that restricting data serves no purpose. If Atlas's natural transparency would calm speculation fostering trust, if Atlas is artificial, the public absolutely deserves to know. Another faction far more cautious points out that confirming extraterrestrial engineering could trigger widespread global panic market chaos of unprecedented scale and profound political instability. Better to verify results privately, prepare comprehensive communication strategies, and release information gradually in carefully controlled doses. The transparency advocates make strong arguments. Science depends on open data and independent verification. Restricting access undermines the entire enterprise, turning research into propaganda where only approved conclusions see the light of day. If Atlas is artificial, trying to hide that fact won't prevent the truth from eventually emerging. And when it does, when Jupiter potentially ignites, and people realise their governments knew something was coming but said nothing, the backlash will be devastating, potentially tearing apart the fabric of society. Better to trust the public with difficult truths than to infantilise them with comfortable lies. The caution advocates counter that truth without context is dangerous. Announcing that an alien artifact is about to ignite Jupiter without the ability to stop it, or even fully understand it, serves no constructive purpose. Markets would crash as investors fled to perceived safety. Religious movements would explode as people sought meaning in cosmic intervention. Political systems would destabilize as citizens questioned why their leaders couldn't protect them. The social fabric would tear before the physical consequences even began. Managing information release, preparing populations, gradually building frameworks for understanding. These aren't censorship, they're responsible governance in the face of an unthinkable cosmic event. Both positions have undeniable merit, which is why the debate remains unresolved, agonizingly paused. And while scientists and policymakers argue about disclosure ethics, the AI models sit idle, capable of answering profound questions, but denied the crucial data they need. Deep inference also introduces disturbing, almost dystopian possibilities. If the AI identifies artificial structures inside Atlas, if it reconstructs the engineering specifications of an interstellar payload, what then? Do we publish the findings, risking global chaos? Do we keep them secret forever, undermining scientific integrity? Do we attempt to replicate the technology, potentially learning how advanced civilizations build planet killers? The replication question is particularly fraught. Reverse engineering alien technology sounds appealing in science fiction, where humanity rapidly advances by studying crashed UFOs or abandoned artifacts. Reality would be far messier. An AI model showing you that Atlas contains exotic alloys or compressed matter cores doesn't magically give you the manufacturing processes to create those materials. It's like showing a medieval blacksmith a diagram of a microchip. They'd recognize its technological nature. They might even grasp the basic concept, but they couldn't build it without centuries of prerequisite development, without the entire scientific and industrial infrastructure that underpins such technology. But even partial understanding could be weaponized. If the model reveals principles behind Atlas's propulsion, or energy storage, or structural engineering, military applications would swiftly follow. Nations would race to develop similar capabilities, not necessarily because they want to ignite gas giants, but because the underlying technologies have countless transformative uses. The same materials that let Atlas survive Jupiter's atmosphere could build unstoppable missiles or impenetrable armor. The same energy storage that powered a century-long mission could revolutionize weapons or defenses. Knowledge that seems purely scientific becomes strategically critical the moment someone demonstrates its application. The knowledge exists to answer these questions. The models are trained, the algorithms refine the computational power available. What's missing is the collective will to confront what the answers might reveal. Because once you know Atlas is artificial, once the deep inference model maps its interior and shows you the engineered core, you can't unknow it. And the implications, the acknowledgement that we're watching an intentional act rather than a natural event, would force decisions we're simply not ready to make. Would we evacuate regions most affected by perpetual twilight? Would we begin crash programs to genetically modify crops risking unforeseen ecological consequences? Would we accelerate space exploration to establish colonies before Earth potentially becomes uninhabitable? Would we attempt to communicate with whoever sent Atlas knowing response times measured in decades, make meaningful dialogue impossible? Would we prepare for war against an enemy that can reshape solar systems with such casual disregard? These aren't hypothetical policy questions debated in academic journals. They're urgent, immediate decisions that require months or years of careful deliberation. Resources we don't have if Atlas reaches Jupiter's core in a matter of weeks. The AI could give us answers. The data exists to feed it. But as long as access remains restricted, as long as institutions prioritize control over knowledge, we're flying blind into whatever comes next. And that might be the cruelest irony of all. We've built tools capable of seeing through planets, of reconstructing composition from light alone, of distinguishing natural from artificial with near certainty. But we won't use them on the one object that matters most. Not because we can't, but because we're utterly terrified of what we'll find. Material science hit a stunning milestone in 2025. Researchers created ultra-dense nano-lattice metals, materials that push relentlessly against theoretical strength limits. These aren't conventional alloys, they're structures engineered at the nanometer scale. Atoms arranged in lattice patterns that maximize strength while minimizing weight. The results approach properties once considered impossible. Materials that rival the incredible strength of diamond while remaining flexible enough to absorb colossal impacts. The breakthrough came from a groundbreaking collaboration between MIT's Materials Lab and a private aerospace consortium. They used a technique called atomic layer deposition, meticulously building materials one atomic layer at a time in precisely controlled patterns. Traditional metallurgy melts metals together and lets them cool, creating relatively random atomic arrangements. This new approach is architecture at the smallest possible scale, designing how every single atom relates to its neighbours. The resulting structures look like microscopic jungle gyms under electron microscopy, intricate three-dimensional frameworks where most of the volume is empty space. But the precise arrangement of solid material creates extraordinary mechanical properties. What makes these nanolattices truly remarkable is their unprecedented combination of traits that normally exclude each other. Strong materials tend to be brittle, flexible materials tend to be weak, dense materials are heavy, light materials lack durability. The nanolattices manage to be strong and flexible and light and durable simultaneously. A cubic centimetre of this material weighs less than a gram but can support thousands of times its own weight without permanent deformation. Drop it from a skyscraper and it bounces. Heat it to temperatures that would melt steel into a puddle, and it maintains structural integrity. Bombard it with intense radiation, and the atomic framework absorbs the energy without cascading failures. This matters because it demonstrates humanity is inching toward capabilities that seemed purely theoretical, the stuff of science fiction. We can't make neutronium the exotic matter hypothesized to exist in Atlas's core. Neutronium exists only in neutron star crusts, matter so dense that a teaspoon would weigh billions of tons held together by gravitational forces we can't replicate in laboratories. But we can now make materials with unprecedented strength-to-weight ratios, heat resistance, and structural stability. The gap between what we imagine for advanced civilizations and what we're achieving ourselves is rapidly narrowing. The theoretical limits of material strength are set by atomic bonds. The strongest possible material would have every atom bonded to its neighbours in optimal geometries, with no defects, no impurities, no weaknesses. Diamond approaches this for carbon. Graphene single-layer sheets of carbon atoms arranged in perfect hexagons actually achieves it in 2 dimensions. The nanolattices extend similar principles into 3 dimensions using multiple elements, creating composite structures where different atoms play different specialized structural roles. Some provide strength, others provide flexibility, others still provide thermal conductivity or electrical properties. It's materials engineering approaching the complexity and elegance of biology. Some of these new alloys even exhibit self-healing grain boundaries. When stress creates microfractures, the material's internal structure reorganizes itself, repairing damage without external intervention. This isn't magic, it's thermodynamics. The lattice configuration prefers a certain arrangement, and ambient thermal energy allows atoms to migrate back into that arrangement after disturbance. Over time, through millions of random atomic movements, the structure anneals itself, subtly closing cracks and restoring integrity. The process happens faster at higher temperatures, which is why material scientists sometimes heat damaged metals to accelerate repair. The nanolattices do this at room temperature, their atomic architecture so precisely tuned that even ambient thermal energy suffices for self-healing. Atlas's uniform thermal signature, that anomalous heat distribution noted by observers, could directly reflect similar self-regulating properties. If the object contains engineered materials with active thermal management materials that automatically redistribute heat to prevent dangerous hotspots, it would elegantly explain why it glows so evenly, despite rotating through intense solar radiation and frigid shadow. Engineering isn't alien in the sense of being incomprehensible. It's alien in the sense of being advanced beyond our current capabilities but not beyond our understanding. Natural objects in space asteroids and comets show dramatic temperature variations. The side facing the sun heats to hundreds of degrees. The shadow side radiates heat into space and drops to cryogenic temperatures. This relentless thermal cycling creates immense stress drives, sublimation, and shapes surface geology. Atlas doesn't behave this way. Its thermal emissions remain stubbornly steady, suggesting either an internal heat source or, more intriguingly, a thermal management system that actively moves heat from hot regions to cold ones, maintaining perfect equilibrium. The nanolattices demonstrate that passive thermal redistribution is possible through material structure alone. High thermal conductivity plus carefully designed geometry equals even temperature distribution without requiring complex active systems. These breakthroughs revive crucial discussions about the prerequisites for interstellar travel. Building a vessel capable of surviving a century-long journey through the void requires materials that won't degrade, won't fracture under extreme thermal stress, won't catastrophically fail when bombarded by relentless cosmic radiation. Ultra-dense nanolattices represent humanity's early halting steps toward that capability. We're proving that such materials are possible, that the engineering challenges can be solved, that interstellar hardware isn't fantasy. The ultimate challenges of interstellar travel aren't primarily about propulsion, formidable though that is. They're about durability. A spacecraft launched from Earth toward the nearest star system, Alpha Centauri 4.3 light-years away, would spend decades or centuries in transit, even moving at significant fractions of light speed. During that unimaginable journey, cosmic rays would constantly bombard the hull, each impact potentially creating microscopic damage. Temperature swings from passing through stellar radiation fields would stress materials to their breaking point. Micrometeoroids, tiny dust grains moving at relative velocities of kilometers per second, would mercilessly erode surfaces. The vessel needs to survive all of this without maintenance, without repair crews, carrying its precious payload intact across distances so vast that communication with home becomes utterly meaningless. Real-world applications for these revolutionary materials are already emerging. Fusion reactor containment vessel structures that must withstand extreme heat and neutron bombardment benefit immensely from these materials. Current fusion experiments use magnetic confinement to keep superheated plasma away from physical walls. But even the most powerful magnetic fields can't contain everything. Neutrons having no electric charge pass right through and slam into the containment vessel. Each impact damages the material slightly, accumulate enough damage, and the vessel catastrophically fails. Self-healing nanolattices could extend reactor lifespans dramatically, possibly making commercial fusion economically viable, unlocking a new era of energy. High G sensors for spacecraft, devices that experience sudden brutal acceleration during launches or emergency maneuvers, need components that won't shatter under stress. Conventional electronics break when subjected to accelerations exceeding a few dozen times Earth's gravity. Military artillery shells carrying guidance electronics already push these limits. Spacecraft experiencing emergency maneuvers or collision avoidance could exceed them. Sensors built from nanolattice materials could survive accelerations that would pulverize traditional components, unlocking new possibilities for space exploration and defense. Deep-sea exploration, where pressures approach those found in Jupiter's atmosphere, requires hulls built from materials that won't crumple like tin foil. The Mariana Trench, the deepest point in Earth's oceans, descends to pressures exceeding 1,000 atmospheres. Specialized submersibles with thick titanium hulls can reach it, but barely always on the edge of structural collapse. Jupiter's atmosphere at the depths, Atlas is targeting experiences pressures measured in terapascal millions of atmospheres. No material we currently manufacture could survive intact. But nanolattices, if scaled and refined, might represent the architectural principles needed to build structures capable of enduring such unimaginable extremes. Every advance brings us closer to a future where humans could build something like Atlas. Not tomorrow, not this century, but eventually. And if we're on a path toward that capability, then civilizations with thousand-year head starts could easily possess technology that makes our current materials look primitive, like comparing a flint axe to a modern supercomputer. The gap isn't unbridgeable, it's just time. Consider the astonishing trajectory of human materials technology. 1,000 years ago, we worked crude iron and bronze. 500 years ago, we developed steel alloys and began understanding metallurgy scientifically. 100 years ago, we created aluminum alloys and early composites. 50 years ago, we manufactured carbon fiber and advanced ceramics. Today, we build nanolattices and graphene structures. The pace is accelerating exponentially. Each generation develops materials that previous generations considered impossible. Extrapolate this trend forward 1,000 years, 10,000 years, and you get materials that would look like magic to us, but represent straightforward everyday engineering to their creators. This raises a profound philosophical question about recognition. When we observe Atlas, when we meticulously analyze its properties and behaviors, are we seeing something utterly alien, something from a realm beyond our comprehension? Or are we seeing a version of ourselves advanced by millennia, but operating on fundamental principles we're just now beginning to grasp? The carbon metal composites, the thermal management, the structural integrity. All of it aligns uncannily with where our own material science is heading. Maybe we recognize Atlas's engineering because it's not fundamentally different from what we're learning to do. It's just monumentally better. There's a concept in archaeology called technological convergence. Different civilizations separated by vast oceans or millennia independently develop remarkably similar solutions to similar problems. Pottery emerges everywhere because clay is available everywhere and fire is universal. Metallurgy follows predictable sequences because chemical properties dictate which metals can be refined with which techniques. Writing systems share structural similarities because they all solve the fundamental problem of encoding language visually. The laws of physics are universal. Chemistry is universal. A civilization evolving on a planet orbiting another star faces the same fundamental challenges we do. They need materials strong enough to build with light, enough to move, durable enough to last. The solutions might look strikingly similar because the constraints are identical. Atlas's engineering, if it is indeed engineering, might be recognizable precisely because it's the inevitable result of solving the same problems we're painstakingly working on. Interstellar travel requires certain material properties. You derive those properties from first principles. You design structures to achieve them. A human engineer and an alien engineer, both working from the same physics, might arrive at remarkably similar solutions. Not identical, the intricate details would vary. But the broad strokes, the fundamental approaches, those might converge. If Jupiter ignites, if Atlas completes its mission, we'll be watching the result of engineering that uses materials we can almost but not quite replicate. And that almost is the most tantalizing yet frustrating part. We're close enough to understand what's happening, not close enough to prevent it. Just close enough to appreciate the terrifying craftsmanship. That appreciation carries a bitter, agonizing edge. We can analyze Atlas's trajectory and infer control. We can study its spectral signatures and deduce exotic composition. We can model its thermal properties and recognize advanced materials engineering. But we can't build an interceptor, can't match velocities, can't stop it. Our understanding has tragically outpaced our capability. We know what's about to happen. We grasp how it works. We appreciate the devastating elegance of the solution, and we're completely powerless to interfere. Maybe that's the real chilling message of Atlas. Not a threat, not a greeting, but a demonstration. A civilization capable of this kind of engineering doesn't need to communicate through clumsy radio signals or pictorial messages. They communicate through sheer capability. They show you what's possible when you solve material science, when you master trajectory planning, when you commit to century-long projects. They're not saying hello, they're saying look what we can do, and by extension, look what you cannot. The gap between recognition and replication might be narrow in cosmic terms, a few thousand years of development, but it's wide enough that we're stuck watching, analysing and appreciating engineering we can't match. Not yet. Maybe not ever, if Jupiter's ignition changes Earth too drastically for technological civilization to survive. The nano-lattices we've created represent humanity's best, most ambitious attempt at exotic materials. They're impressive by our standards, revolutionary even. But compared to what Atlas might contain, they're primitive. The difference between a crudely fashioned stone tool and a sleek multifunctional smartphone. Both are technology. Both represent intelligence applied to matter. But the sophistication gap is so vast that the comparison feels almost meaningless. And yet both exist on the same continuum. Both are reachable through patient development and relentless scientific inquiry. Atlas isn't magic. It's just further along the same path we're walking, and that makes it more terrifying than any incomprehensible alien artifact could be, because we understand enough to know exactly what we're missing. The profound, unbridgeable chasm of time and technological mastery. The final chilling piece of this cosmic puzzle comes from biotechnology. In 2025, scientists successfully engineered plants capable of switching metabolic modes under continuous light. These remarkable organisms, initially designed for Arctic agriculture, where summer brings months of uninterrupted daylight, can maintain photosynthesis and growth without the crucial dark respiration periods that most plants require. They resist circadian disruption, operate efficiently under constant illumination, and tolerate heat stress far better than their wild counterparts. This groundbreaking research began in Norway, where climate change has been reshaping agricultural possibilities in regions once too cold for farming. Greenhouses in Svalbard operating under the relentless midnight sun desperately needed crops that wouldn't exhaust themselves trying to process constant photosynthesis. Traditional plants, having evolved over millions of years in predictable day-night cycles, literally burn out under continuous light. Their cellular machinery overheats. Chloroplasts accumulate damage faster than darkness allows them to repair. Yields drop catastrophically after just a few weeks of 24-hour illumination. The solution came from studying organisms that already elegantly handle this problem. Certain Antarctic algae species that evolved in environments where seasonal light patterns swing from months of profound darkness to months of continuous sun possess genetic switches that toggle between different metabolic states. The researchers isolated these genes, modified them for compatibility with crucial crop plants, and carefully inserted them into wheat, potato, and lettuce genomes. The results exceeded all expectations. Modified plants not only survived continuous light, but thrived under it, producing yields comparable to, or even exceeding, standard varieties grown under normal day-night cycles. This breakthrough suggests something profoundly crucial. Biological systems can adapt to continuous light, or indeed other extreme environmental changes, far faster than ecosystems can naturally evolve that tolerance. Genetic engineering dramatically accelerates adaptation, transforming processes that would take thousands of generations into single-generation modifications. If Earth faces perpetual twilight from an ignited Jupiter agriculture, it doesn't have to collapse into famine and desolation. We could engineer crops to thrive under the new alien conditions. Within years, perhaps a single decade, modified wheat, rice and maize could replace varieties dependent on night. The sheer speed of this adaptation is what makes it revolutionary, a potential lifeline in a cosmic catastrophe. Natural selection, the elegant, brutal process that shaped every organism on Earth, works through random mutation and differential survival over countless generations. It's powerful but agonizingly slow, operating on timescales of thousands to millions of years. Genetic engineering compresses that timeline to mere months. You identify the trait you need, find it in nature, or design it from scratch, insert it into the target organism and test. What evolution would need millennia to accomplish, we can now do in a single growing season. But here's where it gets truly interesting and chilling. If humanity can engineer rapid biological adaptation to environmental extremes, surely an advanced civilization could do far, far better. Genetic modification isn't a human invention. It's a fundamental technology that emerges naturally from understanding biochemistry. Any species that masters interstellar travel has probably mastered bioengineering to an extent we can barely imagine, which means terraforming from their perspective might involve not just reshaping worlds, but reshaping themselves to suit those worlds. Think about what terraforming usually means in science fiction. You find a planet, maybe Mars or Venus, and you spend centuries altering its atmosphere, temperature and chemistry to match Earth. You're forcing the planet to accommodate your biology. But there's another approach, one that might be far more efficient, more elegant. Instead of changing the world, you change yourself. Engineer organisms that breathe different atmospheres, tolerate different temperatures, thrive in different gravity. Suddenly every world becomes habitable, not just the rare few that happen to miraculously match your evolutionary origin. Europa, once melted, would be an utterly alien environment by human standards. The ocean chemistry, dominated by salts and ammonia, would poison terrestrial life. The low gravity, barely a tenth of Earth's, would atrophy bones and muscles in organisms evolved under stronger pull. The radiation levels bombarding the surface from Jupiter's intense magnetic field would shred DNA in unprotected cells. These aren't minor inconveniences, they're fundamental incompatibilities between Earth biology and European conditions. But if your civilization uses biotechnology as casually as we use smartphones, adaptation is a choice rather than an insurmountable barrier. You don't need Europa to be Earth-like. You need yourself to be Europa-compatible. And if you've been planning this for a century, if the probe currently diving into Jupiter was launched by engineers who knew their descendants would colonize the resulting ocean worlds, then those descendants are probably already gene-modified for the environment. Consider the engineering timeline. Atlas launched 100 years ago assuming it came from a star system dozens of light years away. The civilization that built it wouldn't live to see the results of their work. The engineers, the scientists, the planners, all dead before the probe reached its destination. But their descendants, modified through successive generations of genetic enhancement, would inherit the transformed solar system. You're not building for yourself. You're building for versions of yourself that don't exist yet. Versions engineered specifically to thrive where you've chosen to plant them. Continuous light metabolism, the kind our Arctic plants now possess, becomes essential in a system with two light sources. Earth's crops would need it to survive Jupiter's glow. Europa's hypothetical colonists would need it too, along with ammonia tolerance, pressure resistance and radiation shielding. These are solvable problems for biology. Evolution has already solved them in extremophile organisms on Earth. Genetic engineering just accelerates the process. Ammonia tolerance exists in certain bacteria that use ammonia as a nitrogen source. Pressure resistance appears in deep-sea organisms that function at depths where the weight of water above would crush unprotected tissue. Radiation shielding, or at least radiation repair mechanisms, evolved in organisms like Deinococcus, radiodurans, a bacterium capable of surviving radiation doses that would kill humans 1,000 times over. These traits aren't theoretical. They're real, tested by evolution, proven functional. Transferring them between species is the challenge we're rapidly learning to overcome. This closes a profound conceptual loop in the Atlas hypothesis. The mission isn't just about creating ocean worlds, it's about creating ocean worlds that perfectly match the biology of whoever sent the probe. Earth is chemically and gravitationally wrong for them. Europa is perfect once thawed, and the biological toolkit needed to colonize a thawed Europa is probably already developed, sitting in genetic storage somewhere waiting for the right conditions to deploy. Imagine the meticulous millennia-spanning planning. You identify a solar system with a gas giant massive enough to potentially sustain fusion if triggered. You calculate the trajectory needed to deliver a catalyst to the right depth. You design organisms capable of surviving in the moons that will melt when the giant ignites. You encode those designs in genetic libraries, stable storage that can be activated when the time comes. You launch your probe knowing it will take a century to arrive, knowing you won't live to see it succeed, knowing your genetically modified descendants will emerge from suspended animation, or cloning banks, or whatever method you've chosen, ready to populate the worlds you've meticulously prepared for them. The implications for human survival are both hopeful and chilling. Hopeful because we're proving we can adapt biologically to extreme environments faster than we thought. Chilling because if Atlas succeeds, if we're forced to live under perpetual twilight, we'll need to use that capability immediately. No time for gradual adaptation, no luxury of multi-generational adjustment, just rapid genetic modification, deployed at a civilization scale, turning ourselves into organisms suited for a world we didn't choose. The political and ethical challenges would be immense, testing the very soul of humanity. Who decides which modifications to deploy? Who receives them first? Do we modify embryos creating a generation born adapted? Or do we attempt adult gene therapy, changing existing humans at the cellular level? The technology for both exists in experimental form. The social consensus to use it at a planetary scale does not. Atlas would force that decision onto a species barely comfortable with genetically modified crops, let alone genetically modified people. The future if Jupiter ignites won't primarily be shaped by how the planet changes. We understand the physics of that. Fusion pockets, thermal radiation, orbital destabilization. The equations are clear, the models run the predictions made. The future will be shaped by how we modify ourselves to survive those changes. And that's a biological question, not an astronomical one. We've built flash adaptation genes into plants. The knowledge exists. The techniques are proven. Can we do the same for humans? The answer is yes, technically. Should we? The ethics are staggering. Modifying humans means changing what it means to be human. Do we remain the same species after radical genetic engineering? Do we want to? These are questions philosophers and bioethicists have debated for decades in theoretical contexts. Atlas makes them urgent, practical, unavoidable. But the alternative, watching agriculture collapse and ecosystems unravel while we wait for natural selection to catch up, is far, far worse. Natural adaptation to a brightened sky would take tens of thousands of years minimum. Humanity doesn't have that time. Crops would fail within seasons. Food chains would destabilize within years. Civilization would fragment as populations competed for dwindling resources, leading to global conflict. Genetic engineering offers an escape route, a way to stay ahead of the collapse, but only if we're willing to take it to embrace a future where humanity sculpts its own biology. Atlas might force us to answer questions about human genetic modification that we've been avoiding for decades. Not in academic papers or congressional hearings, but in emergency triage centres where modified seeds are being distributed and desperate volunteers are lining up for gene therapy trials. Because the alternative is starvation, widespread death, and the breakdown of everything we know. That's how technologies get deployed when survival is at stake. Not through careful deliberation, but through desperate, terrifying necessity. And somewhere, if this hypothesis holds, another civilization already answered those questions. They engineered themselves for ocean worlds. They built a probe to create those worlds. They launched it knowing their modified descendants would inherit the result. We're witnessing the final stage of a plan that began before any human alive was born. And when Jupiter's glow first brightens our night sky, when we realize darkness is gone forever, we'll understand that the next chapter of human history isn't astronomical. It's biological. It's genetic. It's a profound choice between adapting or fading into irrelevance, while new forms of life claim the solar system we thought was ours. The probe is falling now. The physics are in motion, and whether we're ready or not, whether we believe it or not, the transformation is coming. Not in centuries, but potentially in years. Not to distant worlds, but to our own. And the species that emerges from this transformation, whether modified humans thriving under Jupiter's glow, or Europa-adapted colonists rising from genetic libraries, might look back at us the way we look at our pre-technological ancestors, recognizable, related but fundamentally changed by the demands of a universe that doesn't care about our comfort, only our ability to adapt. And adaptation in the end is just another word for survival.